Hello, welcome back everybody to our whole training series. Today I am again very happy to introduce Shiro Liu, who is the research scientist at NCSA. And today Shiro is going to talk about how to accomplish distributed deep learning on HAL. So he will go over some training materials which will show how to use data parallel training, the data parallel model for training convolutional neural networks. And so with that, Cheryl, please take it over from here.
Hi everyone. Yes, thank you for that for the introduction, and thank you everyone for attending our workshop. Today we're gonna cover how to train distributed models on HAL system using PyTorch API distributed data parallel. So all the training materials for today's workshop is in this HAL shared space. So you can copy them from here. And also, if you want to follow throughout this workshop, you can create interactive sessions using the HAL on demand. Okay, let's do this first. We do have reservations of several nodes for this training. So make sure you have this whole training on the reservations. So first I'll show you how to create the interactive sessions. If you open this web page and do the Jupyter notebooks, and let's do GPUs, we're gonna use 2 hours. Here we have whole training, and let's try 16 CPUs. And because we use multiple GPUs, so here I have 2, and let's launch it. It takes a few minutes. Okay. In the meantime, you can open a terminal and copy the holder. Let's try.
The complete folder path starts with /tmp.
Yeah. So under this /tmp HAL distributed, you will see a folder that contains our training materials. So you can copy this to your home directories. If you do like copy
cp-r, because that's whole folder there.
Yeah. Yeah, to whatever you want in your under your home directory, and you can open in the interactive sessions. Yeah. So once you copy it, and once your interactive sessions are initiated, you can navigate to the folders. So I put everything under here, but yeah, and under the folder there are like 1 Jupyter notebooks and 2 Python files. So we can open this. So in this workshop, we're going to use all 3 files. So I just opened all of them. If you have difficulties to either create interactive sessions or copy these files or accessing these files, just let me know. I give everyone like 1 or 2 minutes, and let me know if you have difficulties.
Hello.
Yeah.
I'm having I'm having trouble finding the folder. Where is it in where am I supposed to find it? I have logged into Hall. I did all the processes we did last week, but I am not able to locate the folder.
Let me show you the folder again.
Please.
I posted in the chat.
Yeah, I just
Okay.
copy pasted
Okay, thank you.
the line that you can use to copy. So Diego, about your question, have you used Hall before? Have you logged in into Hall through SSH?
Yes, I did on my terminal.
Okay.
So you must have specified something incorrectly, like so Shiro, maybe you can show the parameters again in your when you were trying to start interactive session. Not in your Google Doc. Oh yeah, okay, this for example, yeah. So partition should not be GPU, partition should be different, partition should be debug.
Yeah, I guess I just use the GPUs, but you can also use debug.
Yeah, I think this needs to be debugged because this is the only one which is available for this tutorial. This is the one that is set up for us to use. So try Diego, try use this debug partition.
Okay, I'm trying right now. Yeah, I think it gave me the same error.
Did you type in whole training for the reservation?
Yeah, I did put that in name of reservation.
Is this your first time using Hall on Demand, or
Yes, it is.
but you do have accounts on Hall, and
Well, he logged in, so he was able to log in. So it means that he already had it, yeah.
Yeah, I was able to log in. Maybe
what's the error message again?
He posted into the chat.
Oh, okay.
That typically means there is something is not correct in here.
Invalid accounts.
yeah, I'm able
partition.
to see the files in the temp folder HAL distributed.
So, okay, you are able to see it. You just cannot initiate.
Start, right,
Yeah.
the interactive.
But you do have an interactive session, but just not with GPUs. Like how you can open it.
Oh, I just, like, on my terminal, I can see the files. I cannot start the Jupyter
Oh, I see.
notebook session.
So maybe could you try like yeah, I guess if you only want to see these files, open these files, not running it, you can just not using this, try with only CPUs and see if you can start an interactive session like this. And see if you still get the same error about the invalid account.
Yeah, it's still giving me the same error, but yeah, it's okay. Maybe I can just follow.
Yeah, I will try to pin out.
Yeah, by looking.
Okay. Yeah, just email or Slack us after this. I start then.
Okay.
So yeah, this workshop is about to scale into multiple GPUs using the PyTorch API distributed data parallel. This package it's a deep learning framework in PyTorch to accelerate training routines. Today, you will learn about the principles underlying DDP. So our focus will be on distributing the training of the classification network across multiple GPUs. The general concepts presented here are applicable for any model architectures and applications. So the outline of this lab is first, we will give a high-level introduction to this distributed data parallel APIs, and we will give general parallel computing concepts that are necessary to understand a distributed training frameworks. And second, we will give an overview and initial run of existing code base. This existing code is a classification model using PyTorch and the fashion minutes dataset that is built to run on only a single GPUs. So this is a quite easy examples, and that mostly you are familiar with. And then after this, we will do a multi-step refactor of the existing code so that it uses DDP to run distributed across available GPUs, introducing the DDP terminologies and practice. And finally, we have a final run of the refactored code and distributed code with discussions of its speed up. So the learning objective will be by the time you complete this lab, you can learn what DDP is, and also eventually to use DDP to refactor or build deep learning models that trains distributed across multiple GPUs. So the first is the introduction. There are two popular strategies. One is called model parallelism, and another is data parallelism. These are two strategies to train distributed neural networks. So the model parallelism partitions the layers of a given model architecture across multiple GPUs. If you have, for example, a sequential models that are very big, say if you have 10 different components of your model architectures, you can partition the model architectures into, say, 2 GPUs, with the first 5 layers in one GPU and the second 5 components in another GPU. So this is about model parallelism. The data parallelism is different, that it batches the data into smaller disjoint subsets that are simultaneously processed by the available GPUs. So for data parallelism, the model will be identically replicated across GPUs. But the data will be split into the same number of GPUs. For each GPU, the model are the same, but it only processed a subset of the whole data. While it is possible to combine the two strategies for high efficient training, it is common practice to begin with data parallelism. It is because for data parallelism, we only have to deal with partitioning the data. The model will be identical across different GPUs. So it is easier to start with. Also, for large language models like GPT-3, in most cases, we have to combine both the model parallelism and the data parallelism. Next, we'll introduce some terminologies. So the first terminology in a distributed training is a process or a worker, which refers to an instance of the Python program. So each process controls a single unique GPU. The number of processes is the same to the number of GPUs. The second concept is nodes. A node is a physical computing along with all its hardware components. For example, for how each node contains 4 GPUs. And the third concept is called word size, which is a total number of processes participating in training. Or you can think it as the total number of GPUs you're going to use specifically for this lab. And the next is the global rank. Global rank is a unique ID assigned to each process. The process with global rank 0 is referred as the main process. So we just assigned a unique ID to each of the allocated GPUs. And the final is a local rank, which is a unique ID assigned to each process within a node. So here's a plot that can better demonstrate these terminologies. So here, for example, we have two nodes. One is called host 0 and host 1. And in each node, we have two GPUs. For this first node, the two GPUs have a local rank of 0 and 1. And for the second host, the two GPUs also have a local rank of 0 and 1. But globally, these four GPUs across into two nodes has global rank from 0, 1, 2, 3. So after this, we're gonna introduce data parallelism with DDP. So in data parallel training, the model architecture will be replicated across available GPUs, with each GPU being fed a unique slice of data. Training is synchronously performed in a manner such as all the model replicas are parameterized by the same weights. When it comes to setting up the model on each GPU, an important point to note is that weights are initialized only on the main process and are subsequently broadcast to all other ranks. This is done to ensure all GPUs have the same copy of the model parameters before training commences. The DDP addresses this synchronization internally. So all this description until now, it's about the initialization of DDP. So what it does really, it's like it will replicate a model architecture across all available GPUs. And then it starts to initializing the parameters. But initialization of the parameters is only done by the main process. And then this initialized the parameters of the model will be replicated across all available GPUs. So that's the initialization steps. So following the initialization, then it's about splitting the data to sending the non-overlapping subsets of data to each GPU. Then we're going to use a function called distributed sampler, which allows each GPU to independently perform a forward pass operation, yielding a loss value, and then calculate the gradient and broadcasted, which provide an average gradient for each parameters in our model. A backward pass using the average gradient ensures the model parameters continue to be synchronized across all GPUs after training step is completed. So what it describes here is the training process of during the DDP, during the distributed training. So for each GPU, it's fitted with its own slice of data, and then it do the back propagation and to get the parameter updated. And after each steps, the parameter updated, all the parameters across different GPUs will be broadcasted to get an average, and then this average will be broadcasted back to each GPU again. The communication and the synchronization between processes is handled by the initial process group and the distributed data parallel methods. So in the examples we're given, we will go through this step by step. You will get a better idea by then. So let's first start with overview of existing model file. So in the shared folders, you will see a file named fashion-minutes.py. So this contains the model architectures of convolutional neural networks for multi-class classification. So the model is kind of quite standard. We will go through this very quickly. So first is pass some inputs arguments. These are the common arguments like batch size, number of approaches, and learning rates, target accuracy, like when to stop, and patience. So these are just some arguments, common arguments. And then the next is the definition of the convolution blocks. So it's a sequential model that contains 2D convolutions followed by batch normalizations and the activation function. So it's a convolution block. And then we define the residual block. The residual block is composed of several layers. Like we call this class we just defined, and then a job up, and then we have actual layers. All these are pretty standard. If you are not familiar, you can go through this later after this workshop. But they are pretty standard PyTorch models. And our overall network is defined in the wide ResNet. So after the model architecture is defined, then we start training by call the model train, and this is to go through the data. The data we're going to use is the fashion MNIST data. We loop through the train loader to do the forward and backward and model parameter updating. And after training is testing. So we're gonna have some metrics and accuracy measures and return it. In the main function, we download the data. The data is readily available from Torch Vision. And we define the train loader by using Torch data loader. And here we have 10 models, 10 classes in our data. And we call the model functions and define the loss as cross entropy, and define our optimizer to be stochastic gradient. And we start to train it. And finally, after training, we will print the accuracy measures at certain steps. So I just go through this very quickly, but I just want to show you this is pretty standard PyTorch neural net models. We will not spend too much time on this Python file. Instead, we will focus more on this to-do list, to-do steps, which is how to converting an existing PyTorch files that only runs on one GPUs into a code that can run on multiple GPUs. Let's go back to the so after we go through this model, we can run it. Here I just run it quickly. Maybe I run it a little extra more using batch size 256. So for the first time, when we run it, it will have to downloading the data first. But after the first time to run it, we will not see these steps. While we're waiting, do you have any questions? So the model is running. So another thing we can check is if we go back to our I can see I'm using hall 01. So if I can so the printout will give us the cumulative time spent and the speed of image per second. Yeah, we required 4 approaches, so it will finish in a second. But you can see this this simple Python file can work. But here until now, we're only using one GPU. Okay, this is done now. So in the next, we're gonna modify the scripts I just showed step by step. So it can run on multiple GPUs. So our current call to this fashion amnest Py entails the optional specification of several parameters like batch size, number of approaches, and learning rates. In moving to distributed training, it will be important to specify as inputs the number of nodes and the number of GPUs per node. As a result, our call to the function will significantly change. It will be helpful to keep this in mind as we gradually add distributed functionality to the code. Eventually, at the end of this notebook, if we would like to execute in training on 2 nodes with 4 GPUs, we will need 2 terminals on the nodes designated to have ID 0. The following will be our function calls. Right? We specify nodes, a number of GPUs, and number of nodes. So in other words, we will run the scripts on each node, telling it to launch number of GPUs process that all sync with one another before training begins. As you will observe below, part of this synchronization is enabled by the initial process group. Starting now, we're gonna making modifications to the training scripts. So the step 0 is to import the DDP package. So this is simply done by import the torch distributed as this. So if you go back to the Python script, so that's our to-do step 0, which is to include the DDP import statement for convenience. In the solution file, this is to use the solution for each steps. You can try to do it on your own by modifying directly on this file. If you find some difficulties, you can use this file, solution file, as reference. But yeah, for step 0, we just import the distributed. And second, the next step is to add inputs arguments for the number of nodes, the number of GPU per node, and the node ID. We will now expand the arguments accepted by our program to include 3 key parameters. So this is also easily done by just modifying the arguments. So if you go back to this original file, you just simply adding more arguments, follow the last one. In the solutions, you can see we're adding 3 more arguments: a number of nodes, and nodes ID, and number of GPUs. So while the GPU is training, you can also use NVIDIA SMI to track the GPU usage. Because our training, so remember in the interactive session, we allocated 2 GPUs. Now you can see there are 2 GPUs available. So The one is this one, and the second is this one. In one important thing to look at is GPU utilization percentage. Here, because we're not running anything, so it says 0. So if we rerun this model, right, we'll give it a few minutes. And we do it again. Oh yeah, you cannot run both cells in a Jupyter notebooks, but you can do this by opening a terminal and do this NVIDIA SMI in the terminal. And then you will see the utilization will be something close to 100%. If you're using a large batch size. We're going to show you this later. And once the sweep arguments is added, the next step is to determine the word size and specify the nodes associated with the main process. So the word size is the total number of GPUs. In the 3 actual arguments we just added, we have number of GPUs and the number of GPUs per node and number of nodes. So the word size will be the multiplication of these two. That would be in step 2. Yeah, here we're gonna compute the word size and then specify the IP address of the main process. So in the solution file, you can see these 3 actual lines. We calculate the word size and specify the IP address and port numbers by using operating system environments. And after step 2, the next step is to move the training code into a worker method. So when training the model use DDP, we will use Torch's multiprocessing features to spawn an independent process for each GPU. To enable this, we will first move our training logic into a worker method. So shift the training code to do step 3 to a new method called worker. So the goal is to have each process perform the training operation implemented in the work function. The methods to launch a predefined number of processes will be covered later. So in this simple one single GPU Python script, our training is done in the main function, right? Here. But we have to refactor this into a new function called worker function and accept 2 inputs. One is a local rank, and the second is all the past input arguments. So the worker will allows the DDP to spawn on multiple GPUs. So eventually, so in the solutions, in the last lines, you can see we have Torch multiprocessing sprung. We have sprung a worker function by a number of process with some arguments. So the worker function is really kind of like the main function, where it should include all the training steps. So what we do in step 3 is just to define this additional worker. So the specific functions of this worker is in step 4. So next, we'll compute the global rank for each process and initialize the process synchronization. So once the process are launched and the work function within each process invoked, we need to ensure proper initialization and synchronization. So this is done by this initial process group method, which accept 3 parameters: a backend multiprocessing platforms. Here we use NCCL, and a word size, also then a global rank of each process. Again, if we refer back to the solutions, you can see we calculate the global rank. The global rank, which is the nodes ID times the number of GPUs per node, plus a local rank. And then we call this initial process group with 3 arguments: the backend, word size, and the rank, which is the global rank. Okay, so after this step is done, let's look at step 5. So the next step is to minimizing redundancy and facilitating communication between processes. So within a node, for efficiency purpose, we want only one process to download the data. Also, we're going to introduce an actual function barrier. So this is to ensure all the processes in a given node will wait until for the dataset to complete its download. So here it's step 5. We have flag download. So if the local rank is 0, we in a node, we define it to be true, otherwise false. And the data to call this fashion eminence download, this will only be downloaded when the local rank is 0. And then we call this barrier function. So this is to ensure synchronization. So what it does is that it will wait for all the tasks defined above to finish, and before it proceeds to the followings. Yeah, so this is about step 5. And step 6 is about wrap training and validation data with distributed samplers and enable data shuffling. So as we discussed about the 2 model parallelism and data parallelism, the 2 strategies, for data parallelism, each GPUs will only receiving a unique slice of the data. This can be accomplished with this distributed sampler. So for each approach, this function split the datasets into a number of segments determined by the word size. Say if you have 10,000 samples in the entire dataset, and the word size, which is equivalent to the number of GPUs, is 10, then each GPU will be assigned like a tenth of the entire data set, which is 1,000 data samples. Each GPU is then assigned a unique segment to process with a prescribed batch size. Also, another thing to what's loaded is that by default, the shuffle the data prior to evenly divide it into the number of segments. We have to manually change the shuffling patterns at the beginning of each approaches to avoid always using the same ordering. If we do not do this for every approaches, the splitting will be the same, which is what we try to avoid. Let's see how it looks in the code. So after the training and testing dataset is downloaded, here we call this distributed samplers. And to split the data, the download entire data by giving the number of replicas to be the word size, and rank is the global rank. And we do the same thing for testing data. And once we have this subset of the entire data, we wrap it with a data loader to have the train and that testing data loaders. And this is done for step 6. And just manually changing the sampling seeds kind of is by passing the appropriate samplers as a parameters. Okay, so this is about step 6, which is kind of to preparing the data to split the entire data into evenly into each GPUs. And the next step is optional. It's about synchronization batch norm statistics across all process. So the default behavior of batch norm layers in a distributed setting is to separately compute batch statistic for each process. Stated differently, for a given GPU, the mean and standard deviation for normalization are determined with only the slice of the data passed to the device. Therefore, in any given training steps, batch statistics do not capture all the batches processed in parallel by each GPU. So this is not a significant issue when the batch size per device is large enough to obtain good statistics. But in someone's studies, the convergence and performance are negatively impacted if the batch size per device is small. So this is kind of a description of like a small drawbacks of this distributed the data parallelism schemes. Is that when we do the batch norm, if the batch data is kind of big, then the statistics of the parameters like the mean and standard deviations that we used for normalization, they are supposed to be relatively the same across different GPUs. But they will definitely be different because you are feeding each GPU with a different data. At each step, this statistics about the parameters should be different. But if your batch size is large enough, the difference may not be significant. However, if you say each of your data sample is very small and you are forced to choose a small batch size, then to synchronize the batch norm statistics becomes essential. So to do this, we simply just need to convert the regular batch norm layers to this torch sync batch norm, convert sync batch norm. So again, this is optional if for each of the data samples is large and you use as that you're using a quite small batch size. Otherwise, this step is optional. So in the code, we just adding this line, which is to adding this sync batch norm layer. Okay, this is about these optional steps. And in step 7 is to pin process to use the appropriate GPU and wrap the model with distributed data parallel. So in the single GPU settings, we defaulted to using the GPU with ID 0 as a device to store our model and our data. We now need to order this logic to link each process a unique GPU. We call this distributed data parallel method to produce a copy of the model on the designated GPUs. So and finally, to modify the computation for image throughput with a reduced call. The image throughput calculation for single GPU case, now it's incorrect. The first step to properly calculate this matrix will be introduced the barrier, which we called it before, which will ensure our process has completed one's training approaches. We will then perform a reduce operation to sum the image throughputs across our GPUs. Note that image throughput is now effectively the total number of image processed across GPUs divided by the duration of the slowest training approaches. This is done in step 8. So this is only like this is not essential if you want to train in your model. This is more like to measure the speed up of the computation for the distributed training to see like how many times the model is accelerated. So so here in step 8, we call this barrier to ensure all the computation among GPUs are synchronized, and we define the running time and the by adding each epoch time, and with times this batch size divided by the time and dual reduce. This gives us an image per second. And the next step is to calculate average results among workers. So this is to measure the two metrics, the accuracy metric. Since we're not validating the full data sets on each GPU anymore, each process will have different validation results. To improve the quality, we will average the validation results among all workers. Because now each GPUs will give you a different metrics. So here what we do is just to use the average as a good measurement of the overall performance. And that's in step 9. Here I do a summation of this accuracy and loss, and then divided by the total number of GPUs. So that gives us the average accuracy and loss among all GPUs. And we print it out in only in the first GPU, which is with a global rank of 0. So after this step, the last step is to spawn all the process. So this is the last step to do it. So we have well-defined work functions. We just spawn this into the number of GPUs. And that's it about this. All the modification we need to do to convert a single GPU code into a multiple GPU code. Now you can see here we try to use 2 GPUs. We're only using 1 node. And let's see the speeding up. So remember we run this before. Let's see what we use. So we have 4 approaches with batch size 256. Okay. We can use the same thing and see what we got. One thing we would like to observe is the speeding up of this image per second. Here we see like about 1800 images per second by using 1 GPU. Now, since we're using 2 GPUs, ideally we see something around like 3600. And now you can see it's not like exactly around 36, but you can see the image per second is relatively doubled. And that's conclude our workshop for today. By then, I think you should be able to modify your code to parallelize using distributed data parallel. Do you have any questions? You can, if you cannot follow this, you can also practice this after this workshop.
Yes, I have a question, but I'm not sure that if this is the right place to ask this. But so my group has a cluster that we use, and currently there is no we haven't implemented any distributed machine learning training workflow. So I was wondering, like, if we wanted to do that, how does one go about getting the I guess the cluster ready to use the PyTorch distributed?
Your group has a cluster that you want to use. are you planning to use Hall or you planning to use your own cluster?
Oh, so I mean, I think that if we have access to HAL, like, I mean, we could use it as well, but since we do have this like local resource of ours, like I was wondering what would be the process to like what kind of modifications we would have to do. Like, do we need to install the backend on the cluster, like the
Yeah, I guess I don't know about the like your clusters. Is there like a multi-node, multi-GPU cluster or?
right, yes. So it's like, I think around like 15 nodes with 4 GPUs each or something like that.
Yeah, that sounds similar to Hall. This I guess as long as you have like network connections among nodes and within a node there are connections of like GPUs among GPUs. You should be able to easily use this distributed data parallel. This is like a kind of like in PyTorch internal APIs. It's easy to install. You should not feel any like that. It does not require any additional efforts to enable this. But again, I'm not familiar with your system. You are free to try on your system and let me know if you have any difficulties. Or you are free to also welcome to use Hall for your project.
Okay, thank you.
Yeah, you can also email me or leave a message in the Slack channel. If you are working with big models and you would like to try this distributed data parallel, let me know if you have some difficulties. I think we still have like 40 to 50 minutes remained. Yeah, if you can stay here, you can try to like work on the two Python scripts and try to run it on Hall and see if you can run this successfully or if you have some questions.